going well. Okay, now we've got our audience. Everyone's warmed up. You all know what's going on. I know everyone is probably freaking out about their assignment, or potentially the 12 people who are watching right now are the ones who have already finished it and are like, well, I don't have anything else to do. I may as well just hang out at the lecture. But thank you for coming, whether you've finished your assignment or not. Hopefully a few people who are working on their assignments tune in and have me in the background. I don't mind being on the second screen. As long as people are joining me and engaged with the coursework, then it's just wonderful to have everybody joining in whatever capacity they have. So before we get to the content, let's just recall that we were kind of going through these different systems or different terminology about networks. One of them was like, is it circuit switched or packet switched? One was like, what's the protocol for communications? We were talking about what the medium was, transmission medium. We talked about topology. So, we were doing several different, packet switch versus circuit switch, what the topology was, and what the mediums were. And we had a lot of fun with it with ReactNet last time. So this time we're going to have a lot of fun as well. I'd like to play a little video and then we will have a bit of a chat about it. So here we go.
Oh, it hasn't worked. See if I can get it to work. There we go. Probably shouldn't eat on camera, right? We're watching a movie, why not have a snack? Alright. So now, well, I've still got this. That one is not wanted. Audio output capture. Why is it doing that?
Let's turn that one down. How about that? Make sure I'm turned down in all my things. Turn down, turn down. Turn down, cool. Okay, so the question I was asking people on the chat was, let's have a think about the lighting of the beacons protocol. So what's the transmission medium of the lighting of the beacons protocol? What's the topology? And what's the other details? Okay, so Gabe has handily probably answered all of our questions. Transmission medium is, according to Gabe, visible electromagnetic spectrum. So either the flames or smoke. Could be either what we're listening to. And then we were thinking about the topology could be either a ring or a bus. Leopold's just suggested it's a bus, actually. Then we were thinking about if this is simplex, half duplex, full duplex. Gabe has suggested it's full duplex. Yeah, see, I think Isabel's got the right of it here. Isabel's thought is that you can't really have full duplex because if someone lights flames over on the right-hand side and someone lights flames on the left-hand side, you don't know whether a message is going one way. I think Taliesin has got that right as well. I think we're thinking that this is some kind of circuit switch, not packet switched, because we don't really have any. The message can only really be one bit, right? It's either no message or one message. Yeah, so Isabel's correct. If you try to send a message both ways at once, they'll be lit, 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 and then they won't be able to cross because both sides of the circuit are going either side and sort of cancelling everything out. Yeah, so Gabe is suggesting we could have some timing protocol. Yeah, I like this one. The timing protocol to, like you can only have your file lit for a minute. I guess the problem is that with the way that the system is designed at the moment, once you've lit the fire, you can't put it out, right? It's this huge pile of wood. You've poured a bunch of oil all over it, and it's just on fire forever. So we're really not don't have the flexibility of turning this off after a minute. Yeah, now maybe just getting back to the bus idea, getting back to the topology. I think we were right thinking it was a ring or a line. Because on a bus, if it was a bus, then the last person on the end of the sequence of towers would be able to see the first person's fire when it lit. But the whole point of this medium, this idea is that you can't see that far, it's over the horizon, so you have to have multiple fires to be able to communicate the message that far, all the way across the mountains. Yeah, I mean, the one thing that I wonder when I'm thinking about the lighting of the beacons medium is, like, what's this guy's job for the rest of the time? This guy just has to live in the mountains and can't do anything except have to sit there and in case a fire is lit. And they literally are never lit except for this one time. So like this person has spent their whole life up on that mountain, never doing anything. And then like their mother was doing that before them, and their mother's father was doing that before them, and their mother's father's mother was doing it before them. Generations of people have been lighting the beacons on top of this mountain for years. And then finally, like, you know, Gandalf and Pippin just mess it all up. So I suppose save the day in a certain sense, but you'd feel a bit miffed, right? Okay, why don't we get on with the serious content of the lecture. The serious content of the lecture is to talk about two topics really. One is a kind of high-level model of networks called the the OSI 7-layer model, which is important information in terms of trying to break down what has to happen in a big network that might span the whole world, something like the internet. The other topic of this is to look at a lot of examples of different kinds of connections between computers and peripherals, really. We're mainly focused on computer to peripheral connections. And I want to motivate that to start with by a network connection, or really a communications, not really networks in the sense of the internet, but networks in terms of connecting computers to each other, network connection for musical instruments. So the connection I want to talk about for a while is MIDI. And we've talked about MIDI on the forums already, so I'm sure there are people who are quite experienced now with what MIDI is and what you can do with it. It's really two things. MIDI is a way of connecting lots of musical devices together, musical computers, and it's also a way of storing the information which is sent over a MIDI network connection. So a MIDI file is a stored version of all the information going over the wire with some extra details about timing, so it can be all spooled out in the correct timing. So when you've got musical synthesizers or digital musical instruments, there's a lot of digital musical instruments like this keyboard right here, which they don't have any sounds. This one just creates musical instructions. So if you hit this button here, that's telling something else that it needs to play a C. And when you press down on it, it says play a C. And when you let go, it says stop playing a C now. So I call these musical instructions, right? They're just like the dots on a page of a musical score. They're instructions about what musical actions to take. Should you be playing a note? How loud should it be? What should the settings of your effects units be? Or what should the expression settings be? So in this instance, we've got this whole rack of musical equipment. We've got a little controller here, and then there's this thing, and this is actually the synthesizer. That's a synth. That's a keyboard. This is a beautiful synth called a Nord modular, which is not made anymore. I kind of wish I could play with one of those. They're really interesting machines. And then we've got some other stuff here. Not all of this stuff is a synthesizer, but probably some of them are. Some of them might be effects units or stuff for doing other musical jobs when you're performing a show. So I just included this image so that you can see that, you know, in the big real world, there's often this need to plug different kinds of musical computers together. This is kind of a computer. It's got a microcontroller in it, something, probably a lower end one than you've got in your disco board, but a microcontroller still. And this one's probably got a higher end microcontroller than is in your disco board in order to do all of the cool stuff it can do. So these musical computers get plugged together in different ways. You can use, maybe you don't want to have a keyboard controller, you want to have like a wind controller, like a electronic saxophone type instrument, or some kind of new interface like a touch screen controller, or maybe a DJ controller or something. Lots of different options of what a MIDI controller could be. And then at the other end we have systems for making sounds, being synthesizers. So the MIDI medium, the MIDI networking idea, is like an old standard. This is from the early 80s, I think, 81 or something, MIDI 1.0. I forgot what I had after the thing, after the colon there. Yeah, it was introduced in 1981. So an old standard. And the information in MIDI is sent over a medium of electrical wires. And we use a standard for sending information over electrical wires called UART, which we all also know as like basic serial. So serial is a kind of a style of connection between computers where you send one bit at a time, one after the other, in one sense, but it's also like this sort of basic standard for connecting computers together. We often call things a serial connection or a serial bus. And that's just one instance of, well, my phone thinks I'm talking to it, but I'm not. I'm talking about serial, not Siri. So UART is this basic kind of serial bus. You can have a look at this link in Wikipedia or on SparkFun if you want to know more about that. And basically what UART is going to do is you might send it, connect a register to it. So you've sent a word to it, or just 8 bits usually, sent 1 byte to it. And it takes those 8 bits and then sends them out as electrical signals across a wire, one after another. Whoop. Yeah, we're going to do some, Callum's just mentioned in the chat that we're doing some universal asynchronous reception and transmission. So when you're doing this, you know, I had this diagram of like voltage over time before, and this is your wire. And if you want to send like 101, you would go high, low, high. Okay, it's normally starts at 5 volts, so we'd get rid of that one. So this is going to be our UART connection, just sending 3 bits. Now, you might look at this and think, well, how is our system going to know that we want to send 101 and not just O? Because if I was sending just a 0, this would be the same. That would be the 0. How does it know that this is supposed to be a 1? Well, the way that the UART connections work is that we have a start bit, usually, which is going to be here. Oops. And so we know we haven't started our sequence of information until we get a start bit. So that's going to be there. Then we get our 1, that's start. Then we get our 1. Oops, I'll get back to that in a minute. Then we get our 0. And then we go high again. This is called high because it's higher voltage, and then low is ground. So low for start, high for the 1, low for the 0, high for the other one. Both ends of a UART connection have to know how many bits they're expecting. So usually it's more than 3, but like in this instance, let's just suppose it's 3. You can't really do that, but it would normally be 8 or more. 8 is typical. But then we would have this one as our stop bit. So that's going to be a 1 to be stop. So we've got 1 bit to start, 1 bit to stop, and then 8 bits in between for our message, although I've only illustrated 3. And then there's this important thing with serial connections that, this is what makes them asynchronous, this is the A bit, is that both ends of the connection have to agree on how fast the bits are going to be coming in. So if the output is sending them out at this speed, 1, 2, 3, 4, and the input is only reading them, like it might read this one, and then it reads this one, just reading at half the rate, then it will miss this one in between. So they both need to be reading at exactly the same speed. So the speed for MIDI is 31,250 bits per second. You know, yet that's sort of in the mid-range for serial speeds. Like the typical lowest end serial speed is 9,600 bits per second, 9,600 baud. That's like the slowest serial connections. Although you could configure it, I guess, to slower than that if you want to. So MIDI is a bit faster. And what happens is that when one end brings the line low, the other end starts counting, and then it starts sampling at that correct speed so that they end up in sync. So this is why it's asynchronous, because they're not synchronized by a dedicated clock line. They're just sort of figuring out the clock in between them. So we're going to go into a bit more detail about it in a minute, but this is just the medium for MIDI, or the data format on the line. And then what are the actual messages going to be that we send when we're doing MIDI communications? Well, MIDI is very simple. Every MIDI message has 1 status byte and then 1 or more data bytes. And typically there's 2 data bytes. So the status byte will have a status, that's the first 4 bits, or the the high nibble. Nibble is 4 bits. Have you ever heard that terminology before? So a byte is 8 bits and a nibble is half that, 4 bits. And then usually the lower nibble will be the channel or address for that MIDI message that's dedicated to. That's another 4 bits. And then we have a number of data bytes, which will be a 0 followed by a 7-bit number. So typically, right, all of the MIDI status bits start, or their most significant bit will be 1, and that's how you know they're a status byte. And then the data bytes, the most significant bit is 0, so that's how you know they're a data byte. So that means that when you're sending data over MIDI, you're usually limited to only 7 bits of information. Now, if you've got your 2 times tables in your head, you might know that that gives you 128 values, which is what you typically see with MIDI, is that you get like a total of all the note numbers in MIDI is between 0 and 127, and all of the loud and softness, the amplitude levels or velocity is between 0 and 127. Everything's between 0 and 127 with MIDI because of this 7-bit limitation. There's some special kinds of messages where you actually send 2 data bytes that are kind of go together, treated together. One ends up being the top half of a 14-bit number and the other is the bottom half. So there's ways of having somewhat higher precision or a lot higher precision for certain messages in MIDI, but not all the time. So this is a typical kind of MIDI message I've got illustrated here. We've got our first byte is going to be a note on message, and that means that I've like put my finger down on the keyboard and start playing a note. So the status nibble for note on is 9, 1001, and then I want to send this to channel 1. I've actually made a mistake here because if I want to send to channel 1, that has to be a 0. In MIDI there's a total of 16 channels for different to control at once over one MIDI system. So you could have one synthesizer that has 16 different instruments built into it, and then it's being sent a MIDI through one MIDI cable, 16 channels of information simultaneously, or kind of all the MIDI messages are all mixed up. But that 16 is because we've got our 4 bits of information to choose a channel here. So channel 1 is 0, and then channel 16 is 15. So you just have to do that little calculation in your head if you're changing these things. The second data byte for a note on message is going to be the pitch of that note. And MIDI has its own notation for pitches, which is that 0 is the lowest pitch, 127 is the highest pitch, and 60 is given to be middle C in MIDI. So 60 is going to be a C, 62 is a D, 64 is an E, 65 is an F, 67 is a G, etc. And then the third one is going to be a velocity, and that could be called amplitude as well, right? It's called velocity because if you're thinking about a keyboard, it's kind of how fast you're hitting or how hard you're hitting the key down, which is often measured by seeing how fast the key moves up and down. A little mechanism will detect when it's started to be struck and detect when it gets to the bottom and work out the speed of that. So that's why it's called velocity, but you can also call it amplitude. Yeah, so this is a MIDI message. Now, so far we haven't really seen anything happening, so we're going to have some fun now. I'm just going to prepare for fun. Just getting this old thing to work. I haven't done very much like work in the physical world in this class yet, but we certainly can have some fun, and we're going to, in this, why won't this work? I've got a GoPro here, but it keeps turning itself off. I think I need to tell it to start recording, otherwise it won't. Whoops, I got it to work before. Okay, well it's... Yeah, okay. I'm just going to unplug its HDMI for a minute and make sure I know what's going on. feel like it might be the cam link which is not working. I know I'm a person who has trouble with their streaming rig, so okay, here we go. Let's give that a go. All right, so I have to just turn it to. It's kind of annoying that the GoPro doesn't just do this automatically for me. Okay, cool. I'm just going to tell it to start recording, even though I don't really want it to record. Just means it doesn't turn off. Okay, so here's my desk. Thank you for joining me here in the real world for a few minutes. And what I'm going to do is do a bit of serial communication with this microcontroller I've got here. This is an Arduino. If anyone's messed around with microcontrollers before this class, chances are you were using something more like this, one of the Arduino microcontrollers, which is the Atmega microcontroller chips, rather than one of the STM microcontrollers like we use in the disco board. And the reason is that these ones are very cheap and very popular. Some people think that they're like kid stuff and everyone should be using the STM ones, but they're a lot of fun and they're generally pretty easy to use. So I don't know if I've got lost all my audience now. People seem to be not asking any questions. Maybe you're all working on your assignment. You might come back later. Now I'm just going to just point out what I'm using. Here's my microcontroller. And I've also got here an oscilloscope, which is going to let us visualize one of these serial messages. So if I just turn back to my, you're chatting in Twitch. Oh man, I need to open my Twitch window. I think I'm back on the screen now. You should be able to see what I'm doing. I've got my little Arduino program here set up. I'm in VS Code, but I'm not using assembly to program my Arduino because I'm not a masochist. I only use assembly when absolutely necessary for learning something important. I've got my Arduino system set up here. By the way, like if you're programming Arduino, it often comes with its own little IDE, which is sort of like disgusting now. Now that you can do it with Platformio and VS Code, I'll never go back to the Arduino IDE. So I've got two little things in here, two functions. One is, by the way, this is the default way that the Arduino is set up. It runs a function called setup to start with, and then it runs a function called loop. Now, and then it runs loop over and over again, just like your main function in your programs for the disco board. So if we look in the setup function here, the first thing I do is set up the serial 1. So that's the Arduino's first serial port. And I said serial1.begin and gave it the data rate that it needs to use, 31250. So if we had a look in the source code for serial 1, it would be doing a lot of the things that you have to do when you set up the hardware on your disco board, like start the system clock, start some kind of bus to the peripherals, and then it would probably start a UART peripheral, probably a USART peripheral, as some kind of serial peripheral that's built into the chip, which can do both synchronous and asynchronous serial. And then it tells it gives it its configuration, says, okay, you're going to use one start bit, one stop bit, 8-bit frames, 8 bits at a time, and then I've given it one parameter to give it the speed. That's easy enough. Probably hard if we had to do it in assembly, but easy enough to do here. And now in my loop, all I'm going to do is write this byte, 00, once to the serial port. It's going to just spool out that byte in serial and then delay for a second. Actually, I might change it to a different one. Let's change it to 0F and give it a go. So I had all kinds of problems getting my my Arduino to work earlier in Linux just because of Linux stuff. I'm going to see if I can get it to happen now. So I'm flashing. Okay, that should be good. Go back to my desk. You should be able to see what I'm doing now. And now if I've got my oscilloscope here, and I just want to make sure that I've set it up so that it's going to trigger or stop the screen when it sees this certain pattern going down. So when the voltage goes from 5 volts to 0 volts, 5 volts is this line up here, and 0 volts is this 0 line down there, then it will stop. At the moment it's already stopped at a previous data point, so I'm just going to press OK, and it should stop again immediately. And it did. So now we get a picture of 1 byte on the coming from the Arduino. So there's the start bit going to 0. Then we've got 1, 2, 3, 4 bits at high, they're 1s, then 4 bits at 0s, and then we have a stop bit which is 1, and then it rests at high again. So that's our output from this single bit, which is neat. So now we can maybe try something else and just see if we can identify what's going on. If you just remember what I asked it to do, I was trying to get it to print out 0F. So is that what I've got here? 0F. Just remembering what we were thinking last week, you have to make sure that the bits are in the order that you expect. So actually here we've got, instead of 0, 0, 0, 0, 1, 1, 1, 1, we've got 1, 1, 1, 1, 0, 0, 0, 0. But that means that we're in little endian order, which is probably correct, right? Just as we were doing this with the ReactNet last week, you have to make sure that your endianness is correct when sending data, and in serial, the default is that it should be little endian coming over the serial connection. Okay, maybe I'm going to try something else. I'm just going to, for kicks, do 01, 01, 01, 01. And I'll compile that, send to the board. It's just doing its job right now. Okay, it's sent to the board, and I'll just set the oscilloscope again and see what we get. Okay, so now I wanted it to do 01, 01, 01, 01, and I've actually got 10, 10, 1010. So that makes sense, doesn't it? We've got these 8 bits in that amount of time. If I just bring this right up to you so you can see how this works, we can just have a bit of a think about how many bits we get per unit of time. As you can see, I've got this little grid here, and I've set this up on the oscilloscope. You might not be able to see it, but I've set it up so it's the grid left to right is 50 microseconds per division. So if I just count this off, we've got kind of, for the 10 bits, we've got 1, 2, 3, 4, 5, 6, 6.5 divisions. Oh, I just accidentally reset the power plug is really bad on this oscilloscope. Also, world's worst oscilloscope here, so I'm sure there's engineers in the audience who are groaning right now. This certainly happened last year. People were groaning at me. So that was 10 bits of information, the 8 bits plus 1 start and 1 stop, in 6.5 divisions. So that's 6.5 times 50. That's 325 microseconds for 10 bits. So that's 32.5 microseconds per bit. So now if I divide that 1 divided by 32.5, that's 0.0307. I'll prove it to you. Oops, that's upside down. 0.0307 bits per microsecond, and then multiply that by 1,000,000 is 30,769 bits per second. And I guess I wasn't exactly right, because I'm just eyeballing like a tiny oscilloscope screen. But that's close enough to my goal bit rate, which was 31,250 bits per second. So it's really working. Having fun with hardware today. Now let's get this to do something useful. I don't want to get it to just show me dumb bytes that don't make any sense. And I've written here on my screen another little routine, which is just going to send three bytes. It's going to send a status byte, a data byte, and another data byte. So I don't know, Gabe was saying something in the chat. Have to have to have an oscilloscope that isn't a hacked $5 logic analyzer. Exactly. To have a decent oscilloscope, but that's what we get. I only use it once a year to do this lecture, so, or I could use it for other stuff, but I haven't quite yet. So I've got my status byte and 2 data bytes. That's going to be the command byte, pitch, and velocity. So now I'm going to use my little function that I've set up, and the first bit is going to be OX90, so that'll be a note on, and then the pitch is going to be 60, and the velocity is going to be 127. 127. It's not OX60, sorry, it's 60, regular 60. Okay, because see, I need to put that at the end. Okay, and now I might actually want to turn this off as well. I might want to turn this off after a second, so I'm going to add in OX80, which is going to be a note off, and then I've got to give it the same pitch, so note off on that pitch, and then usually a note off message has a velocity as well, which I can just give it a 0. Don't ask me why note off has to have velocity, I'm not quite sure. And I'm going to delay after that. So here's my little loop of doing those two things. Okay. Oh, it failed. Uh-oh. What have I done wrong? I hope it hasn't failed because of... maybe I need to put that first. Oops. I don't have it in a header file, I'm just using it when I see it. Is that going to compile this time? Okay, good. All right, let's go back to the desk. So it should be doing its job now, sending these little messages. Let's see what happens when I trigger this. Hey-oh, getting some more interesting stuff going on. So I could probably zoom out. I'll just change the to 0.1 milliseconds per division. Maybe 0.2. There's my whole frame. Oh no, come on. Oh well, that's booting again. Anyway, maybe we could also do something slightly more interesting with this. Give me a message. What's going on with you? No, I've set this into the wrong mode. Now I'm in trouble. Hold off. Okay, forget that. We're going to do something interesting with this information. We're sending these MIDI bytes, and now I'm going to take my MIDI cable, which I plugged into my Arduino with all these little wires. All you need for this is the one wire that this information is going across. This is the blue one. And then you need a ground wire, and then you also need a 5-volt wire, which is not really used for anything except just to, it's just part of the spec. So I've got a little synthesizer here. I'm going to turn it on. Sounds like it's doing something, right? I might use a slightly more interesting patch. Glass pad. Oh, that's boring. Organ. This is a little FM synthesizer by Korg called the Volca FM. Okay, some synth brass. So back on my screen, I might just try a different note, right? What if I tried D? Or we could do... do a D and then a G and then alternate those two. We'll see how that goes. So I'm going to upload the new patch. All right, this is sounding a lot like what you probably have to do in your sounds like what you have to do in your assignments now. So maybe I should stop teasing you with beautiful C++ where you've got all these things. You've got a delay function. You don't get a delay function in your assembly program, do you? You have to find some other way to schedule a note to be in the future. And of course, I'm not using any kind of data structure to store these two notes. I've just got them as instructions in the instruction stream. So this is bad program design. Don't do this in your assignments. I guess you can, but it's not considered to be the best way to do things. But that was just a little bit of fun messing around with MIDI and basic serial UART. Now, I guess I should say that although it's a bit of fun right now, it's very soon going to become serious business, because in your assignment 3, you actually have to start to make some network connections over little wires, just like I've got on my desk. These little wires connected to something. And you're going to get some little wires and plug them into your disco boards. And of course, you probably don't have an external synthesizer unless you do, to test things out, but you can also connect the wires like right back into your disco board itself and practice some of these techniques with a little network protocol which we describe how to do in assignment 3. So that's going to be a little bit of fun for you to have as soon as you finish handing in your assignments tonight, isn't it? Oh, how mean. Making you guys all do this. If you'd like to, just going to go back to small for a while. Now we've had our fun. If you'd like to go through this later, I've got some screenshots of exactly what this kind of stuff looks like. There's 0, OXOO, OXFF, OX01010101, OX10101010. And yeah, that's all for our little MIDI thing. So thanks for going on that little journey with me on my desk. I hope it was fun. So we're going to talk about a few more concepts and then go into this 7-layer network protocol idea. So I talked a little bit about what a serial protocol was before. So we've got this concept of serial versus parallel. So in serial, the data is going to be sent one bit at a time over a line, just like on our example I was showing you just before. And parallel is another way of doing things. Instead of having just one little connection between the two computers, one line connecting them. Oops, I want my pen. We get lots of them. 1, 2, 3, 4, 5, 6, 7. Parallel connections aren't that popular now. It used to be like when I was a kid, every computer had serial ports with just this kind of UART serial and parallel ports. And the parallel ports were always used for printers for some reason. I don't really know why. I guess I should research antique computers and understand that stuff. But you know, parallel was cool because for each instance of sending a bit of data, you could send a number of lines at once. And in fact, it had a lot of lines connected together. But it turns out in the long run to be slower because you have to set all of these lines in sync and then send some message that's like, okay, now is the time to read it. And that process of kind of getting everything in sync, reading it, turned out to be slower than just like making your serial port really, really fast. So all of the ports that you now use for your computer, they're all USB. What is that? Universal Serial Bus, right? There's a lot of serial protocols that can send data one bit at a time and just go super, super fast. So yeah, serial versus parallel. Of course, nothing wrong with a parallel system. And if you're designing some little interesting networking protocol or data link protocol between two computers, then parallel is a perfectly fine way to do it. You can use that in the assignments if you want to, in assignment 3 and for other little designs you might want to do. Timing and synchronization. So I was talking about UART, Universal Asynchronous Receiver Transmitter. And there's also USART, universal synchronous / asynchronous. So there can be two modes for doing communications in a serial bus or a parallel bus. And the asynchronous version is what we were looking at with MIDI. So in the asynchronous version, both ends have to know how fast they're going. And then you have some kind of start bit that's like waving the start flag at the start of a race, saying, okay, start counting now and tick in through all of these bits. Then the other option is synchronous, where instead of both ends having to keep time separately, they have a second wire connecting them, which is for a clock line. So the clock line can just indicate where each bit is supposed to be. So in this example, coming from SparkFun's website, SparkFun's a great little electronics store in the States. On the upwards edge, the rising edge of all of this clock signal, that's telling the receiver to read data off the data line. So it reads 1, 1, 0, 0, 1, 0, 1, 0. And in this case, like, we don't really need to have the start bit and stop bit, because we can just wait. The clock line can just stop when it doesn't need to be reading data anymore. So that's asynchronous and synchronous. It's kind of weird that, asynchronous seems like, I don't know what I'm talking about, but I guess when I'm thinking about it, I get confused between them, which one is synchronous and which one is asynchronous. But asynchronous is like no clock, a without clock. So that's the way I remember it. This is the same information. There's lots of important ones which use synchronous connections, and a really important one is called SPI, which we'll talk about a little bit later. And then asynchronous, also lots of important networking connections like RS-232 have independent timers. So just to take a little bit of a break, give my voice a second, maybe you could think about where the ReactNet example has led us astray compared to how you would implement protocols on a disco board. So I'm going to sip my coffee for a minute and you can make a suggestion. What's like completely unrealistic and stupid about the ReactNet example we did on Tuesday? I guess if I had to say something that was unrealistic and stupid compared to between ReactNet, apart from like everything, but with ReactNet, we had like all of these different symbols, right? You could choose whichever React emoji you wanted. There's like a million of different emojis. But with these real serial connections or real networking connections, we've only got 0 and 1. So you have to, yeah, someone just said using emojis, yeah. Exactly, so Isabel's come up with something important there. I'll just bring the screen up so people reading the video later can see where we're up to. So whenever we wanted to have a new kind of message in our ReactNet system, we just added a new symbol, a new emoji. On the disco board, you have to do everything in binary. And that kind of means that you have to decide exactly how you're encoding information and sending it beforehand. And I think that the MIDI protocol is instructive here, because like bytes can be a number and they can be a letter. And then like MIDI has to make all these different kinds of messages, and you only get bytes to do it. So you have to be kind of clever about how you organize what bytes mean what, right? And so the designers of the MIDI spec made some decisions in 1980, before 1981 when it was released, in the late 70s, early 80s, about what messages they were going to send and how they were going to be encoded into bytes. So they decided. And you know what? They made really good decisions, because we still use MIDI today, right? I've got this synthesizer I bought the other year, uses MIDI. I've got another synthesizer on my desk, uses MIDI. You want to store your beats in Ableton Live, guess what? It's using MIDI. So they made good decisions in their protocol, and their protocol was to say the first bit of the byte is going to say whether it's a data byte or a status byte, and then the status bytes have these number of different options, and the data bytes have something between 0 and 127, and the interpretation of what the data bytes are depends on what the status byte is, so you've got to have a little state machine to make sure you work out which byte or match what the status byte is and take the correct information with the subsequent bytes. So you have to make these decisions about your protocol, which is how you interpret these bytes beforehand so that you can send them across the wire. Okay, so now we can move on. Sorry to start talking more about waxing lyrical about MIDI again. So far we've been building a vocabulary: topology, asynchronous, medium. Oh, what else did we do? But circuit switching, packet switching, symbols, binary. We're going to get a bit more formal with some kind of higher level information about networks. So what we're going to look at is the so-called 7-layer OSI model. It's a bit of a mouthful. This is the Open Systems Interconnection model, and it's a conceptual model for characterizing all of the functions of computer systems that might be in a network. And I'm talking now about not just connecting one computer to another in your house or connecting a synthesizer to another synthesizer, but of networks which could be that small, but also be the internet. So all the different scales of network. And this is an old thing. It was standardized in 1977 for networks. So it's kind of old news in some ways. The other way it's old news is that although it's instructive and helps us to understand some of the problems about having a big network, like why would we even need to have 7 layers in an architecture? The reason is because networks are really complicated. There's lots of different problems to address, and maybe you start dividing those problems up, then you get at least 7. You end up with about 7 layers, or 7 different responsibilities for different things to have. The problem is that it's never actually implemented anywhere in full. Like the most common networking system for the internet, right, is TCP/IP, which does not use the OSI model. So you could kind of ask, if you were asking me, well, why do we have to learn this? I would say, that's a very good question, but tough luck, you have to learn it anyway, because it's one of these things which is part of our standard education, which we just all have to be aware of. And it is helpful and it is interesting, so we get to take that perspective as well. Now, when you're looking at stuff to do with the OSI model, actually, I don't normally say this, but the Wikipedia article on the OSI model is extensive and useful. So go and have a look at it. It's useful to keep things straight in your head when you're looking at the OSI model. We're going to go have a look at each layer. So here's the 7 layers of the OSI model. We're going to look at this diagram in the next few slides. And here's some kind of view about like how these layers surround our data as a user. So you might be sending some data. You want to send 1 byte to someone else across the internet. This is going to be where your data is stored. And then at every other layer, it's going to start adding stuff around your data, all surrounding until we get right down to the bottom. So the 7 layers of this, starting at the bottom: physical, data link, network, transport, session, presentation, application. So the physical layer, like that's just sending bits across the wire, right? That's how our serial connections are built in terms of electronics, what voltages we're using, what kind of encoding we're using for our bits. And in some ways, that's a lot of what we've been talking about so far, living in this physical layer. What's the medium? How do you say what a bit is? How do you know when your frame of information has started and stopped? And that's all in the physical layer. Then we start adding these other layers on top that do different things. We'll go through them all individually. the point of this diagram is like this person trying to send this packet over to someone else. So on their computer at their end, in their house, they've got all of these layers present in some interpretation. And then out in the internet, in between their two computers, out in the infrastructure of our network, we don't need all of these layers. It doesn't know about these top ones. It only knows about the bottom ones. So this is like in the internet. And then at the other user's end, then their computer has to have all these layers present as well. And then their computer decodes it and slowly peels away all the other bits of information until they're left with the bit of information. Maybe it was an email that was being sent between them. So let's go from the bottom, the physical layer. So this is transmitting raw bit streams over a communications channel. So how do we convert bits into an electrical or optical signal? That's what the physical layer is all about. Some examples of this is like Ethernet cables, right? Wi-Fi connections, that's physical layer, defining how you're going to send raw bit streams over communications channels. The serial connection, the USART peripherals, and the wires going between your computers. So I guess the physical layer is not just the wires exactly, but also the hardware at each end, which has to deal with how that information is encoded onto a wire or another medium and then decoded at the other end. Second layer. So now that we've got some kind of way of sending bits across a stream, we have to find some way that we can send a group of them or a frame of data over this physical link and hopefully do so reliably. So the data link layer has that responsibility. It's supposed to be making sure that the information is going onto the wire, it's received at the other end. You might have some little extra discussions between people at both ends of the wire, but it's sort of still in your house in some sense. It's all within the one local network, one computer talking to a second computer. And if we want to talk like outside of your house, like you send a message to your router that connects to the NBN, and then that message goes across the NBN to some other person's router. Oh, we need to get a little bit further than that. We need to be in the network layer first. Even to send it to your router, your packets need to know who they're supposed to get to, right? So this is the network layer. The previous layer was just like, you can send it to either end of a wire, but the assumption is that the message is, well, we don't know who the message is for, we don't know what we're supposed to do with it. And the network layer gives us some information about who is getting that packet. So you could be sending a message to the router that has to go no further than that. It's only going to the router. It could be that it's going to another computer in your house. Maybe you're streaming data from your phone to your TV and you want to send that data stream. Doesn't go directly to your TV unless you're using Bluetooth, I guess, but it goes through your Wi-Fi router, then back to your TV. So that's the network layer, organizing, routing, addressing, switching, making sure that everyone on the network has an address, make sure that packets get to the right place of who they're designed to get to. And the typical routing network layer example is IP, Internet Protocol. That's the one we always use. Now, if we want to get outside of your router to someone else on the big bad internet, we have to have a transport layer. So this is going to transfer data between hosts where it might not be a direct connection. I guess if you're sending something to your router and it has to go to your TV, your router does have this level of transport layer at the same time. Flow control and congestion control. Good question, Isabel. Let's talk about that later. On the transport layer side, your two hosts, as in two people trying to send a message, have to be able to find each other across a network which might have a lot of different nodes in it, and they're all connected in a different way, and it has to somehow get that information through this network of nodes and make sure that we haven't had any errors occurring. So some examples of transport layer protocols is things like TCP or UDP, which is what we typically use on the internet. The UDP is this kind of low, lightweight version of this idea where you know someone else's address and it just sort of sprays out a message and doesn't know whether it gets there in the end. It's called Universal Datagram Protocol. TCP is much more clever, so it knows to do error correction. So we typically do networking with TCP IP over the internet, and if a packet is lost as it's traveling through the internet, then the TCP transport layer will be able to recognize that fact and make sure that it recovers from it. So now we get a bit higher level. So we've dealt with making connections between different computers or making the low-end connections. We've dealt with how we're going to send data. We've dealt with whether we need to have error correction. We dealt with how we navigate between lots of different hosts. But at each host on each level, we probably want to send more than one packet. We might want to send a bunch of packets or stream a bunch of data. So in that case, we need to have something called a session. So the host at each end will make an agreement and say, okay, I'm going to be talking to you for a while, so I want you to remember about me, and we're going to make sure that we optimize how we're sending data to each other so that we are doing so in a sensible way, quickly. We're not having to keep reopen the connection and keep saying hello to each other. So this would be sort of session establishment. It said, hello, I'm over here, I want to be sending you some data. The other guy says, okay, I'm going to receive it, send it on over, and then they send the data. Then at the end of that session, the guy's like, well, time to go. Seems like you got all my data okay. The other person says, okay, I got it all, see you later, and then the session's over. So that's the session layer. Now we get to the presentation layer. We're almost at the top, where like so far, we haven't really paid attention to what the data is. We've just assumed that once it gets to the other end, we know what to do with it. But what if, for instance, I was sending some data from a disco board in memory on my disco board to someone else's computer, and the other person's computer only dealt with data in big endian format? Or we were sending ASCII data and the other person's computer only uses Unicode. Then we would have to somehow convert what we're doing with our data at the other end to make sure that it's understandable by the other person's computer. So there's a few examples where this will be important. One is that one about like what kind of letters are we sending? Are we sending ASCII letters or Unicode letters or other UTF-8 letters? And is the other person going to open this file and just find gibberish that they can't understand? So we have a presentation layer that can sort of make sure that the data is in a uniform format when it goes onto the wire, and then when it comes back off, it goes back into the native format for that computer. The other example would be some kind of encryption, end-to-end encryption, so that it's encrypted at one end of the host at one end, sent across the wire, in encrypted form, so no one else can tell what it is, even if they're sitting in the middle. They're in the middle, and they're a man, so it would be called a man-in-the-middle attack. And even if they grab this information in the middle, or a person-in-the-middle attack, I suppose we could say, if this person in the middle was snooping on this information, they wouldn't be able to understand it because it's encrypted at the presentation layer, and it doesn't get decrypted until it gets back to the other person's computer. One more layer, layer 7, application layer. So now finally, we have a layer for sending the data to the actual user applications that the people are running on their hosts. And this could be like a little bit application specific. It depends on what you want to do with your data. But how about this one? Every time you open a web browser, you type in HTTP. And that's a protocol for networking, a networking protocol for sending information over the wire. And that's where this lives, at the application layer. Other good examples is things like FTP, right? If you're sending files across the internet. Or SSH, if you're logging into a computer remotely, you're using the SSH protocol. Or SCP, if you're sending files to GitLab. Generally, if you're sending files to GitLab, I think it uses SCP to transport them if you've set it up with an SSH, with a Git address. Someone could yell at me in the chat if I'm wrong. You might have some protocol for discovering everybody on your network. So we often use one called ZeroConf on local networks, so that like your phone can discover what your TV is. How does it know that your TV is there? Because your TV has this protocol where it sends out messages periodically to everybody on the network saying, hi, I'm a TV, I can do these things. And that's got this protocol, ZeroConf networking protocol set up. So this is all of our 7 layers. Now I'm just going to go back a little bit and let's think about where we kind of stood with what was happening at each layer. So I said that these ones here was like, these are the layers which are necessary for everyone on the internet to know about. All of your routers and hardware in between your 2 hosts. Physical, data link, and network. So all the routers and everything sitting out there on the internet, where you're not necessarily sending your information to them, but your information is going through them on its way somewhere else. They have to know how to transfer packets to different people and route information. They need to understand addresses so that they can send that through the internet. The transport layer, this is a little bit difficult to work out the difference between the transport and network layer. The transport layer is only working between the 2 hosts, so the person sending the information all the way to the person at the other end. They need to have a transport layer implemented. There was a question about this difference between flow control and congestion control in Teams. I'm just going to bring that up and let's see what was happening. So Isabel asked a great question. What's the difference between flow control and congestion control? So I think that Mitchell is right here because the congestion control was like out in the big internet. We need to make sure that no one router is overwhelmed by data. Because if everyone was going through one router, that router would overheat and burn up or something, I don't know, or just stop sending data and people would be delayed. There might be lots of other routers hanging around that are free and open, ready to receive information. So at the network layer, which is what those routers out in the big internet can do, they can figure out ways to redirect packets to a router which has capacity. So that's the congestion control. Now, the flow control bit doesn't happen out in the big internet. It only happens between my computer and your computer. My computer is streaming a message and your computer is receiving it right now. But my computer can't send the whole video at once, right? Because I'm recording it, the video isn't over yet. It has to split it up into little bits. And you know, my open broadcasting system is trying to keep control of how fast that data is going out. It's got a clever way of doing it, which I'm sure I don't understand. But that's to do with flow control because it needs to be slicing this little video, which ends up being gigabytes in size at the end of the day after 90 minutes of lecture. It slices them up into little bits that it can send across the internet one at a time. And the little bits are small enough that are manageable by all of the routers that need to be doing congestion control and all the hardware links that are going between different things. And you know, amazingly it works, right? I can keep streaming to you. There's a little bit of buffering so that we've accumulated on each side and at the various servers in the middle. But the hosts at either end are knowing they need to both send a little bit of information, then wait, then send a bit more, and the other one at the other end, at your end, is receiving a bit of the video, playing it back, receiving a bit more, playing it back, etc. So that's flow control. Oh yeah, some good ideas from Mitchell here. Maybe the sender can only send 1,000 bits per second. The sender can send 1,000 bits, but the receiver can only read 100 bits a second. So sender needs to slow down to do it. If you want to know more about how the internet works, I think you should take 3310 when it comes around again, networking at the ANU. I haven't taken it, so maybe I should crib the notes for 3310. I think it's running this semester, and keep up with that important information. 7 layers. Callum says he can recommend 3310. A few of my tutors are taking 3310 this semester. Who is the lecturer for 3310 right now, Callum? Maybe he'll tell me in a minute. I'm quickly running out of time because we were having so much fun with MIDI this lecture. So I'm not going to go too far. As Marcus, yeah. I think it's it's great in some of the later year courses. When you get to the 3000, 4000 series courses in your degree, whatever degree you're taking, there are people who are teaching them who are just teaching like stuff that they are absolute experts in. It's their field of research, their field of expertise. Something like COMP2300, I love this topic. It's really fun, but it's kind of like general to everybody to know about this. But it's really exciting to take a 3rd, 4th year course and really dive into it. So TCP/IP. I told you before that the OSI model was potentially troublesome because it does not match up with our actual way of doing things, and here is how. The TCP/IP protocol, TCP/IP stack, has a physical layer, okay, that's Ethernet, and then it really only has 4 layers: application, transport, IP, and network. And this is a diagram from Uwe that shows that the networking layer kind of has some of the responsibilities of the data link and network in OSI, and the IP layer is sort of part of networking, and the transport has a bit of the session as well, and the application also has a bit of session, so it doesn't quite match up, which is a shame for the OSI model, but this is sometimes the way in computing, that people have a beautiful idea about how to build a framework for something, and then everybody just goes for some other cheap, crazy way of doing it that just ends up winning. But that's not to say that it's TCP/IP is not great, right? I think it's beyond the wildest dreams of the designers of TCP/IP how we use it today, with this fantastic giant internet that everyone's connected to, sending like real-time video streams to each other all the time. It's just probably unthinkable to people at that time how you would do it. There are, although, I should say, examples of OSI compliant systems. One of these is AppleTalk, which was a competitor to TCP/IP. And AppleTalk, I think, has not existed since 1997. Is that right? I'll just look on Wikipedia. It was if you bought a Mac in the early 90s or late 80s that was networking, you probably didn't have the internet. You were probably just talking to other Macs on your local network for a business or something. Then you would use AppleTalk, which is now old and definitely finished. You can figure out when it was discontinued, but by the time we got to the late 90s, it was really on the ropes. It was not something that was going to be continuing. But AppleTalk does have this perfect OSI compliance. It's all worked out. There are probably engineers out there who would say AppleTalk, oh, so beautiful, this is the way everything should be done, but too bad, it didn't win at the end of the day. It's kind of cool that there's some old different physical layers. We tend to only use a few, or we have different physical layers now, but it's either like Ethernet or Wi-Fi. There's many Wi-Fis. Wi-Fi. There's lots of different versions of how to do wireless networking, but the wired networking is a few standards for doing different speeds. It's not as rich these days as it used to be. yeah, as someone's just mentioned in the chat, I think Bianca said, it's now AppleTalk is not supported anymore. It's definitely old news. There was some way to do, like in the death throes of AppleTalk, there was a way to do it over IP so you could exist on the internet and kind of replace the bottom 3 layers of IP, of AppleTalk with the bottom 3 layers of IP. And that would mean that you could work in, given that the big internet has everybody out there in the internet supporting these 3 lower layers, physical, data link, and network, and they use the IP protocol for those, then your AppleTalk system could just pretend to be talking like everyone else is talking, while secretly behind the scenes at the host-to-host level sending AppleTalk messages instead of TCP/IP messages, TCP messages. So that would be cool. Yeah, I think I might stop here and we can talk about SPI, Serial Peripheral Interface, next time or on Tuesday, just before we get into some stuff about operating systems, because I'm sure that everyone wants to go and brush up on their assignments. Please, 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 right now, if you're working on your assignments and listening to me right now, make sure you've committed your code. Please make sure it's pushed up. Make sure that your design document is pushed up. Like people, every time we do an assignment, there's folks out there on Piazza at like 11:30 p.m. saying, oh, I can't get my design document. Oh, the CI job doesn't work. Like by the time it's 23:30 tonight, I'm turning my emails off because like that's stress that we just don't need. We just have to make sure that everyone is working it out now. If you have a last minute question, like pretty much now is the very, very last time that you can be asking a question and expect someone to answer it. And even then, it's getting a bit late. Bianca just said, a bit confused by serial. I missed some of the explanation. Oh, should I go back for a minute? Let's we can check that we're in serial world. Like in the old versions of these notes, no one did serial. But I'm now doing it because I like looking at it through the little camera, seeing it on the desk. Bianca, you can always look back at the recording on Echo 360 or on YouTube. Don't know what's going on here. Ah, here we go. This is a serial message. This is basic serial. That's what we're talking about when I say serial. And this kind of connection is cool because you only need like 1 wire for the signal and 1 wire for the ground, right? 2 wires. And I had this on my little Arduino on my desk. I had a wire for ground and a wire for data. And this was called asynchronous because there's no clock line in between the two computers communicating. They both just have to agree on the speed that they're going to send bits across the wire. So normally the wire is like high, 5 volts or 3.3 volts or whatever the level is. With MIDI it's 5 volts, just so you know. And then one computer wants to send a message, the TX computer, transmit computer, wants to send a message, so they take the line low. And that means that the message is now started. And then at the agreed rate, for MIDI it's 31,250 bits per second, at the agreed rate, they change the voltage of that line according to the bit that they want to send across it. And they've agreed that they're going to send 8 bits, or the programmers have agreed on either end. They can't actually transmit this information across the line. It has to be pre-agreed. 8 bits usually though, for 1 byte per frame of information. So the start bit, then they spool out the 8 bits, and then there's a stop bit, and then the line is idle. And if they wanted to send another byte, they can, at that point, do the stop bit and then do another start bit right there. And they have this little, you have to have this bit, the stop bit and the start bit, so that the clocks can keep in sync, because they might not be really accurate. It may not be really, really accurate. The two computers might have slightly different speeds, and we can't expect them to kind of keep in sync for very much time. But they can keep in sync for 8 messages, definitely. So we That's why we have the start bit and stop bit. Sometimes you also have some like parity bits, so you can work out do a bit of error correction by calculating the parity of your message and putting that after the message itself. So you might have 10 bits, 8 bits information, 2 bits parity, then the stop bit, then the start bit, then the next 10 bits. Bit of discussion in the chat over there. The suggestion from Mitchell was, oh, this one's also serial. That's actually true. This one's like what I think of as like traditional serial, RS232. And this one's more like what we've got for SPI. Also serial, but this is a 2-wire serial connection. This is just one wire, one important wire. One wire. This is 2-wire. SPI is actually a 4-wire connection because it goes both ways. So this is a serial connection too. There's lots of serial connections, right? That's all that means is that your connection is sending 1 bit at a time in a row. But like sometimes we say, if I just say, oh, if you've got a serial port on that computer, I don't mean USB, I mean an RS232 port. And if you say, oh, does your microcontroller support serial? You would say, okay, it's got 1 2-wire serial bus and 1 SPI bus. I think actually on the disco board, it's got 4 SPI buses, so it can do 4 SPI connections, and I don't know how many regular. Maybe that's the total. You can configure it to be either like RS232 or SPI on the same peripheral. The chip on the disco board actually has like built in a component for doing universal synchronous asynchronous receiving transmission, which can either be an asynchronous serial connection or a synchronous serial connection, depending on how you configure it. It can run at whatever clock speed you want. I tried to make it work on my disco board and then realized that it was going to take a lot of time. I may as well just use my Arduino instead. If anyone gets it to work in their assignment 3, then you get a thumbs up. So, so it would be really tricky to get that to work in assembly. Yeah, any other crazy questions? I can see it's a bit frustrating because I say serial and sometimes I mean like messages coming one after another, and then serial meaning a serial port and cereal meaning something you eat for breakfast. So difficult word. Anyway, I'm going to call that a day. We can talk more about SPI serial buses on Tuesday and also talk a little bit about operating systems. Good luck with the assignment and have a great weekend.